All right, stat students, I am at school now. I'm in a workroom, and we're going to continue this lesson. So let's go to, let's talk about the next question, which is number 53 here. And it says, which of the following statements can be true or can be made about on the basis of this computer output? So we have another topic here. We're going to talk about r squared now, okay? This value called r squared. So we have, it's called the coefficient of determination, is the fraction of variation in the values of y that is accounted for by the line of y on x, okay? Now this is a topic that can be confusing, all right? And I want to have the AP stats guy. I've shown videos of his in this class before. Do I have my camera on? I do not. Hold on one second. Desktop. There it is. Okay, sorry. The AP stats guy sort of sounds like Coach Harris explained this, but let's go ahead and write down this definition for and formula for this coefficient of determination, okay? And we see that on this r squared value. This is for the ice cream and temperatures. We have this r squared, so r, and all I have to do to get r squared is just square r, okay? But of course we have this formula right here, which if we compare to the standard deviation, is slightly different, okay? This is the average y value minus, or it's every y value minus its average over our residuals squared, which is this. So these look very similar in most regards, but let's go ahead and write this down. Okay, so let's talk about how we use this to answer this question, because that's what we have on here. That's what this is. This r squared, it's 69.7%, and ours for ours is 91.68% for this ice cream. So I'm going to have the AP stats guy explain this, and it's going to be it's 10 minutes. So, but it's a great video to help explain this. I'm actually going to hide my camera so that you can hear this. So I'm going to go ahead and let it play.
All right, here we go. We're going to talk about r squared in context, okay? R squared is the square of the correlation coefficient r. So remember we talked about a video about how that r is calculated, right? You put in like, you know, you put in the x and the y, and then these guys are all positive, these are positives, those are negatives, that whole thing, right? Okay, anyway. What is this r squared thing, and why do we have to put it in context? Well, it tells you pretty much about the predicting power of your model, but it's also misinterpreted a lot. I'm going to talk about some things that it's not, also about what it actually is. So I'm going to tell you a tale of two pizzerias. There are two pizza places in my town, Gino's and Bob's. So right off the bat, you probably have a different style, Gino, Bob, right? Different kind of places. Anyway, Gino's Pizza, cheese pizza is $10, so just for plain pizza right off the bat is $10, and every topping costs 50 cents. Bob's cheese pizzas start off at $10, but he differentiates his topping prices. For instance, meat's $1, veggies 50 cents. When you double something, it's only 25 cents. But a special like lobster or exotic cranberries, that would be like $1.50 per topping. So all of his toppings aren't exactly 50 cents each, but you know, whatever. So what happened is I sat outside of Gino's for 7 days, and people came out. I said, what was the price? How many toppings? So we get, yes, sir. How many toppings? 4. What was the price? Okay. How many toppings? 3. What was the price? And I collected all of this data, all of this hundreds and hundreds, and I got this scatter plot. I fit a line to it, and I found it. It matched perfectly. It was weird. And then I went over outside of Bob's, and I was like, hey, how many toppings? And they'd say, 4. Well, how much? Put the price, and I made a list of the number of toppings versus the prices. And I made a scatter plot, and I noticed that there was some scatter, but there was still a trend. I noticed in both restaurants, the more toppings, the higher the price the pizza would be. Even at Gino's with the scatter, the more toppings, the higher the price the pizza would be. And in both of them, the equations were similar. As a matter of fact, let's say, well, whatever, let's say that they were a little bit different, but I found the equation for Gino's was, it was $10 for a cheese plus about 50 cents per number of toppings, per topping. And at Bob's, it was $10 per cheese and about 64 cents per topping. But the big difference wasn't just their equations that were a little off, is the R squared here at Gino's was 100%, and the R squared here was only 72%. Now, this is what R squared is not. This R squared does not tell you the percent of times the model will predict perfectly. It does not tell you the percent of points that the model actually goes through. Okay? It doesn't tell you any of that stuff. Okay? It's more complicated than that. Okay? It's not just like, oh, if you have a model with an R squared of 72.72, 72% of the time you're going to make a perfect prediction. No! The model's probably never going to be perfect, except at Gino's, which this is never going to happen. You're never going to, almost never going to get this, okay? So, but this is just for example purposes. But if you have an R squared of 72%, you can use the model a million times and never predict perfectly. Okay, so don't think. It just gives you, it kind of gets you up in there, and I'm going to explain it right now. So this is what it means. First, you need to understand the word variability, and we call it differences. So when I think of the word variability, I think differences, how things differ. So I'm going to tell you what this R squared means. Please listen. Now, we know that prices of pizza vary. There's variability. There's differences. We know that when the people came out, every pizza came out, there was variability in number of toppings, differences. What this R squared means is the following, that 100% of the differences in prices can be explained by number of topping differences. Okay? Because basically the sole reason why prices differed, okay, could be explained by the number of toppings. So knowing the toppings alone, basically the only reason why there were two different prices in pizzas was the number of toppings alone. Just knowing that. So what you say is 100% of the differences of price can be explained by differences in toppings. And we actually use the word variability. So what I say is 100% of the variability in pizza price at Gino's is explained by the variability in toppings. Now, some people like to change it to 100% of the variability in price is explained by the model, because actually 100% of the variability in price is explained by the model. But how do you use the model to explain things? You put in different toppings. So variability in toppings. So basically, prices differ here because toppings differ. I mean, it's not cause, but it's explained by, okay? Even though we know in this case it does. But over here at Bob's, it's a different story. While the model does explain some of the price differences, notice at Bob's you can have two pizzas with 3 toppings but different prices. So while the model does explain 72% of the price differences, it doesn't explain all of the price differences. There's other reasons besides number of toppings why 2 pizzas might cost different, have different things. Because what's the other thing? So think about this, ready? 72% of the price differences can be explained by differences in the number of toppings. 72% of the variability in price can be explained by variability in number of toppings. 72% of price differences can be explained by the model. That's the R squared, okay? What about the other 28%? The other 28% are in the residuals. Here, the residuals are the unexplained. I don't know. I don't know. I can't explain. The model doesn't explain that part. The residuals is what's left over after the model does its job. So you put in 4, boom, boom, you get that, but the model didn't predict this guy. Those little residuals are what's left after the model does its work. Notice here, 100% There's nothing in the residuals here because the model explains 100% of these differences. But only here does the model, over here the model only explains 72% of the differences. Now to oversimplify what's actually happening, you can kind of think about this, okay? Here's a pizza here, and here's a pizza over here. These pizzas have different prices, right? And here are their price differences right here, okay? What did the model of this difference, let's see what part of that difference the model explained. The model said this guy should cost, the one topping should cost this much. And this 5 topping one should cost this much. So the model said this much explained this much of the differences between the two. But see this little part and this little part? That part of the differences was not explained by the model. So while the model did explain a lot of the difference, a lot about the difference between these two pizzas' prices, the model didn't explain all of it. Some of it is in the residuals. It's unexplained. So basically what the R-squared value tells you, it tells you the percent of the variability in Y that's explained by the model. Okay? Notice what it doesn't tell you. This comes up. It says, this will be in a multiple choice. It'll say 72%, the R-squared value of 0.72 means that 72% of the price is explained by the model. No! 72% of the differences in price. 72% of the variability in price. Not 72% of the entire price, because there's part of that entire price that's not explained by toppings at all. What's the part that's not explained by toppings? This initial 10 bucks. That initial 10 bucks is a big part of the price that's not explained at all by the model or by the number of toppings. So the R-squared value is the percent of these differences explained by these differences, not the percent of the entire thing. So you can say R-squared. So you say this R-squared percent of the variability in Y is explained by the model. Notice I didn't say R-squared percent of the entire Y. Just R-squared percent of the variability in Y is explained by the model. Okay? So you say R-squared percent of the variability in Y is explained by the model, the rest is in the differences, or in the residuals. Or R-squared percent of the variability in Y is explained by variability in X. R-squared percent of the differences in Y is explained by differences in X. That's what R-squared means, okay? Hopefully that clears some things up, but that's how you can interpret it in a sentence. Good luck. Keep your head up. You're going to pass this test.
All right. So he did I think a really great job of hopefully giving you an idea about what R-squared is. We're definitely going to write down, I'm going to type in here, we're going to edit this, and we're going to pull back up just that sort of second to last clip where he's talking about how we can interpret R-squared.
A lot about the... this comes up. It says, this will be in a multiple choice. It'll say 72%, the R-squared value of 0.72 means that 72% of the price is explained by the model. No! 72% of the differences in price. 72% of the variability in price. Not 72% of the entire price, because there's part of that entire price that's not explained by toppings at all. What's the part that's not explained by toppings? This initial 10 bucks. That initial 10 bucks is a big part of the price that's not explained at all by the model or by the number of toppings. So the R-squared value is the percent of these differences explained by these differences, not the percent of the entire thing. So you can say R-squared. So you say this R-squared percent of the variability in Y is explained by the model. Notice I didn't say R-squared percent of the entire Y. Just R-squared percent of the variability in Y is explained by the model.
So that's the key. That's the ticket. That's what we need to answer this question. Okay. So when we're looking at this, we're saying which following statements can be made based on the basis of the computer. So this question, if we read the examples, it's talking about the variation, right? And we see these percents here. And what we're interested in is the 69.7%. That is r squared. That's what that is. Okay. And we say, we know 69% of the variation. Now, this is going to be in context. In his context, it was of the prices, right? But here, what's our y value? It is eggs, right? The number of eggs. So we know this can only be B or D. That's all that it can be, is B or D. So then what we're looking for is it to be, it needs to say the model, right? The linear regression is based on the fish's length, right? That's the explanatory variable. So we're going to see which one does this better. Egg production can be accounted for by the linear regression, the model, of egg production on fish length. Okay? So, and then this one here, okay, I think this one is wrong because it says the variation of fish length, but that's not what we're looking at with that r squared value. We're looking at the y value. So this is x and this is y. So that's why B is the best choice for this. Okay? All right, lastly, we're talking about the residuals. Which of the following plots of residuals versus fish lengths? Okay, so remember we looked at residuals. So we compared our residuals to look like this. So I'm going to take a little snapshot of that. Grab my snipping tool. Good here, yeah. Okay. Grab the snipping tool, and we're going to grab this chart, and then we'll compare it down here to the other. All these charts. Okay, so we're looking for which one matches it the best. Automatically, A is not going to work. Okay, that does not have nearly enough on the bottom. Okay, when we're looking at B here, that one looks pretty good. Again, they should match up with these X values, right? So we'll see if that one is good. Here, this one doesn't work. It does not look right. This is not very accurate to what ours is shown. At 4.5, we should have something above it. So B isn't good. C isn't going to be good. There's not enough on the bottom. Is there another one? No. Okay. So we've pretty much declined. Okay, so this is D. D is going to be the best choice just based on what this looks like. So hopefully that makes sense when we're doing those comparisons there. All right, so there's one more question that I want to talk about. I don't think we did any predictions, interpolations, or extrapolations. Maybe I think we did maybe a little bit, but I want to work one more question, and we'll wrap this up. Okay, so we're going to be looking at numbers 44 through 47 on the problem set, and number 47 is the one where we're doing some extrapolation, but we're going to be talking about this. So below is a scatter plot with a least squares regression line, or just a regression line, for calories and protein in grams in 1 cup of 11 varietals of dried beans. The computer output for this regression is below the plot. Okay, wait, computer output. I don't see that, but okay. It says, which of the following statements is correct interpretation of the slope? Well, we know it has to be positive. Okay, so if we see anything negative, that would be a problem. But we're going to be relating this to from calories to protein. So as calories increase, what typically is happening with protein? Well, we should be seeing a positive trend. Okay, a positive trend. So, and it should be. We talk about an increase in calories is causing the increase in the proteins, grams. So in this one, I automatically, because the way that these are worded, okay, and we say predicted, right? What are we predicting? Well, we're predicting the protein based on the caloric value. So we're never predicting calories. So C, D, and E, automatically, we kick those, okay? So then we have to decide, okay, is it 1 unit increase in calories, the predicted protein content increases by how many grams? So we're kind of doing a estimation of slope here. So I took a little screenshot here. What's happening as I go from 600 to 630? Okay, how much is that increasing? Well, it looks like it's just about 4.2-ish, or excuse me, about 2 grams is what we're seeing over 30 calories. So that would be the change in X. So I'd say 2 divided by, divided by 30. So we're in this 0.6 range, which that's pretty close. So B would be the best choice. So we're going up about 0.06 grams of protein for every 30 calories, or excuse me, for every 1 unit, every 1 calorie. So that's why we choose B on this one. That's that slope, okay? Next, which of the following best describes what S 3.37648 represents? Now, that should tell us, or this is the standard deviation anytime you see X, but which one best describes this? Okay, well, it is the standard deviation of residuals. That's what that formula was when we were looking at that. It's the standard deviation of the residuals. That was literally what we put in our definition. That's what S always means. It's the how far they are from the from what it should be. So D would be the best choice on that one. Let's go on to 6. So the circled point on the scatter plot represents lima beans, okay, which have 621 calories and 31 grams of protein. The residual for lima beans is, well, we just want to know, for instance, if we put it on a residual plot and we highlight it, we said that the y value, that y coordinate is the residual here. What would it have to be on this one? Well, we know it's negative, right? Well, how far down, and this should be the y value, right? It's negative. Well, it's not a very large number. B is going to be the best choice here because it's only going down. This is grams of protein, right? It's down about 4 from here, okay? About 4. So that's why that is. It would not be negative 37. That's not going to show up on this graph. Okay, next. This is the one with the, this is extrapolation. Okay, that means we're predicting outside of the range of values. And that's what I want to talk about. Normally, if you had a line, you could just plug it in for X. But let's see what they want here. 1 cup of dried soybeans contains 846 calories. Okay, which of the statement would be appropriate? So I guess we're trying to predict the protein content for these soybeans. So 846, does that show up here? Well, that's not on the graph, right? Not on the graph. So does that cause a problem? Well, yeah, we don't have the line continuing that far, and we also don't have an equation to help us with that. Yeah, so E would be the best choice here. It's not appropriate to predict the content because it's beyond the range of the data, okay, and that model, okay? So that would be an example of trying to make predictions. I kind of wanted one more. Let me see if I can find one real quick. Okay, so I'm just gonna have to use our example with the ice cream. So you'll see this here. I'm gonna hide the residuals here. So if I wanted to predict if it was because this is a 25, what if it was a 30 degrees Celsius day? I don't know how hot that is, but that's probably very hot, I imagine. So a 30 degrees Celsius day, what would we end up with? Well, we can use this equation, this negative 159.474 plus, then we have, oh wait, what? 159, let me retype that. Plus we have 30.0879. And we're just going to put in 30 as that's the Celsius, that's the explanatory variable. So what do we expect? $743 in sales. Okay, that's what we expect. That's what this line is predicting. So it was 614 here. So if we added in those sales, that's what should line up perfectly with this line. That's the prediction, at least. So that would be an extrapolation. An interpolation would be doing the same thing, but instead of the 30, we put a value that already exists, or that's within the range. So let's hold on, let's see this. So we don't have one for 21 degrees Celsius. So let's try 21. So 21, that's 472, which should be right on this line here, 472. If we drew that line, that's where this is. So that's our interpolation. That's a prediction within the range of values if we wanted that. So that's the difference between those. Okay, I'm about to wrap things up here. But I do want to say one thing. There's a question that I want to get rid of in the problem set. I don't know if I already did it. I don't think I did. There was one that I definitely wanted to get rid of. It was I think it's number 60 in here that I wanted to remove. Yeah, number 60 for sure. Yeah. Number 60 we're getting rid of. You do not have to do it in either class, AP or dual credit. So that one's gone, so don't worry about it. Okay, I'm going to stop the video there. If you have any questions, please reach out to me. The problem set is due tomorrow night.